some, some metal parts with me today. So if you do have the option for the side-by-side mode in Zoom, not all versions of Zoom have it. You'll be able to see both the slides I'm presenting as well as some of the real parts I have with me today. I'll also be using polls throughout the webinar. Feel free to engage. It gives me a better idea of who I'm talking to, keep you engaged. I hope everyone's staying safe through this interesting time that we're living in right now. I'm glad we're still able to talk about 3D printing and additive manufacturing. So let's get started. Today we're talking about different additive manufacturing possibilities, specifically in the heavy industry. So let's get started. We'll start. Oh, also I should mention that my colleague Ilya, who's on the line today, he will also be showing some parts for me today. I'll cue him to show them, and you should be able to see we're testing out a new high definition camera that he has to really show you in detail some of the parts we're going to be talking about today. Let's get started. So first, I just want to start with a quick poll. I'm curious, what 3D printing equipment do you own? Feel free to select as many as you have. Just give me a better idea of who I'm talking to, what maybe you're familiar with, what you have experience using. Just give you a couple seconds here to answer this. All right, here, let's see if I can see the results now. Great, so it looks like, a fair amount of you are familiar with FDM printing, some SOA and SOS. Some of you with no experience, or don't own any equipment, but you may have some experience. Some metal powder users as well, great. All right, this is great to know, thank you. All right, let's get started. So Desktop Metal was founded in 2015 with the goal to make metal 3D printing accessible for engineers and manufacturers. I want you to really remember this accessibility part of this mission statement. We're really aiming to make this technology usable for all users. So that really shines throughout this presentation, I think, and as you see in the parts, a lot of the value sometimes is how easy we make this technology for manufacturers and for engineers. So we have 4 different printers now. On the far left, you see a fiber printer. We just announced that that's a carbon fiber printer, composites. The studio system and the shop system, we'll be talking about both of those today. And then on the very, very high volume, we have the production system. So like I said, we'll be talking about the studio system. That's our office-friendly metal 3D printer. The shop system, this is targeted at machine shops for batch production, fully dense, really high quality parts. So the agenda today, we'll talk a little bit just about the promise of what metal 3D printing is. We'll talk about what some of the current challenges are with metal 3D printing. We'll talk about the approach that Desktop Metal took, which is additive manufacturing based on metal injection molding. We'll talk through some applications, and we'll look at some case studies and talk about how the systems were able to add value to these companies. So the promise of 3D printing. If you have plastic printers, FDM, SOA, you're probably familiar with some of these. So the ability to rapidly prototype. But with metal, we're not just prototyping for form and fit, but now we're actually able to prototype, what we call functional prototyping, where the part can experience high loading, high heat, chemicals. We're actually able to test the part in its application to see how it performs and iterate on that. We're also able to do part consolidation. Many parts today are designed for their manufacturing method rather than for their application. So with a part consolidation, we're able to take something that maybe it was 20 different parts, and the only reason it was made out of 20 different parts was because it was easier to make each of those parts and then assemble it than it would be to make them all together. But now with 3D printing, more often than not, it's easier just to print all those parts all together. And we'll look at some examples of that today. Kind of going hand in hand with that is the ability to do these complex geometries that are just not achievable with traditional manufacturing. A part like this, we'll also talk about this later, but it experiences some complex internal channels that we're really able to optimize the part for its application. Something that just wouldn't have been possible with traditional manufacturing. But with 3D printing, just printing layer by layer, it's easy. Since 3D printing doesn't involve any tooling, we're able to do design customization, on-demand design customization, where, we print one part today. If we want to add a logo or if we want to make custom changes to that part for, a certain customer, we're able just to upload a different file. That part starts printing that day, and, we're able to just customize that part which really helps, for the end user, we're able to deliver exactly what they want. The ability to produce rapid tooling. Tooling is often one of the most expensive and longest lead times parts to get. So the ability to print that tooling, especially out of some of the harder tool steels, is a huge advantage of metal 3D printing. Then there's this idea of on-demand manufacturing. Currently a lot of companies, they have these large warehouses, they're stocking tens of thousands of parts just because, a customer may call them up, they need to supply that part to them. They have to order in quantities of 100 or 1,000 in order to make it economically viable to order that part. With 3D printing, the part cost isn't going to change if you're making 1 or making 100. So we're able to, on-demand manufacture, where a customer calls and they ask for a part, we're able just to print that part and ship it out to them in a few days. We'll look at some examples of this today as well. Kind of going hand in hand with that as well as this re-engineering of the supply chain. This will take some more time to really happen, but you can imagine a world where we have printers located throughout the world. And if they need a part in Australia that was designed in Canada, they simply send the file to Australia, they print it right there. Trillions of dollars are spent every year shipping metal parts around the world. So you can imagine if we could just, email files, that would save so much money, so much time. So, as these printers become more and more available in the field, this is something that we'll start to see this real re-engineering of how the supply chain actually works. So looking at traditional metal additive manufacturing, some of you said you're familiar with metal powder processes, powder bed fusion. We saw that this process was really too expensive, too slow for broad adoption. It doesn't have a familiar materials palette. There's no 4140, there's no tool steels. The cost is extremely high, both in CapEx as well as, you have to integrate your facilities. It's very labor intensive. There's not a lot of automation involved. And the machines are just generally pretty slow. So for powder bed fusion, you're really only seeing broad adoption, in the very, very high end of parts, in the aerospace, in the medical places that, they can afford this high CapEx, they can afford this high part cost just because of, how high the quality of parts need to be. So we looked at this and we said, how do we create a 3D printer or 3D printing options that has that on-demand appeal? There's no special facilities involved or highly trained operators needed, and has this broad palette of familiar materials that engineers are familiar with working with. And how do we offer a path for them to also produce in mass production, which is something that wasn't offered, traditionally with metal 3D printing. So our solution was to build 3D printing systems that revolve around the chemistry and the supply chain of metal injection molding, or MIM. Metal injection molding is a powdered metal process. It's been around for 50 plus years. It allows you to create a wide variety of different shapes at a very low cost, utilizing these inexpensive metal powders. It has widely accepted and validated standards, ASTM and ISO. So it's really been utilized across many industries. Automotive, medical, everywhere has kind of been using metal injection molding. It's a great way to make small parts at low cost. So we looked at the metal injection molding process, which, you start with your metal powder, your metal injection molding powder. You mix it with a polymer binder, which is like a glue. That creates your feedstock. You then inject that into a mold, very similarly to plastic injection molding. What you get out of that is what we call a green part. It's that combination of metal powder and that binder, that glue. We put it into a debinder. That's a solvent wash. It's going to remove almost all of that binder material. And we put it into a furnace. The furnace is going to get up just below the melting temperature of the material, and you're going to boil out that last bit of binder, and the part's actually going to sinter and become a dense part. So we looked at this process, which is a well-established, well-known process. We thought, how can we adapt this to printing? So today we're going to talk about two systems, the Studio system, which is the world's first office-friendly metal 3D printer, and the Shop system, which is the world's first binder jetting system designed specifically for machine shops. So starting with the Studio system, we looked at that metal injection molding process and we adapted it to printing. So rather than creating a powder feedstock, we create rods. We did this so that they're safe to handle. There's never any exposed powder. We then simply print the part so you don't need any tooling. So rather than having that mold to create your shape, we're simply just laying down the part layer by layer, the same way you would with FDM process. We then take our printed part, We put it into the debinder. That's going to remove most of that binder material. And then we go into the furnace where we're going to remove that last bit of binder. Your part's going to sinter. Starting with the printer is, it's FDM printing process, or FFF, depending on, what terminology you like to use. But this allows designers to have, very familiar design guidelines. It's a very safe printer. It takes office safe materials, so there's no powder handling involved. Those rods come in a cartridge. You simply just put the cartridge in the overhead bin, like an inkjet printer, and you're printing your part layer by layer, similar to any FDM printer that any of you own. Then we move to our debinder. Our debinder, again, really made to be very accessible. A low emission design, automatic fluid distillation and recycling. The parts go into the debinder dry, they're lowered in, the fluid comes in, washes your part, removes that binder, and then your part comes out of the debinder dry, so you're never exposed to any hazardous chemicals. And then we look at our studio system furnace, which is really the first office-friendly sintering furnace. It fits through a doorway, doesn't require any complex venting scenarios, and then the temperature reaches 1400 degrees Celsius at its peak temperature, which is, an ideal temperature for sintering metals to really the highest mechanical properties. So what's the result of this? We're getting what we call, a near net shape. This is resolution, accuracy, surface finish, that's all quite similar to casting. If you look at this picture here on the right, the original cast part on the right, and then on the left is the part that was printed on the studio system. So we're getting, similar properties to casting, similar tolerances to casting, similar surface finish to casting. From there, right, once we come out of the furnace, we're working with a metal part. The part behaves very similar to if it was cast. So any critical dimensions can easily be, achieved by CNC machining, EDM grinding, or EDM, wire EDM or sinker EDM, post-processing like grinding. So you're really able to achieve those critical dimensions or critical surface finishes if you need. You can even do that mass finishing methods, tumbling or media blasting, even something like welding or heat treating. Totally possible. Once the part comes out of the furnace, it behaves very similar to any sort of metal you're used to working with. So we're working with a variety of materials with this machine as well. Starting, with 17.4, very common stainless steel, great for a wide variety of applications. 316L, another common stainless steel, better for corrosion resistance and better at higher temperatures. Nickel-based superalloy 625, also known as Inconel, great for very, very high temperature, high loading, great for specific chemicals as well. H13, which is a tool steel, has excellent hot hardness, very good for injection molds. 4140, a common low alloy steel, also great for tooling. And then copper, high purity copper, which is great for those electrical and thermal parts that you need. Great conductivity. So just a little recap on the studio system. We're really looking at an office-friendly metal 3D printer. There's no hazardous powders at any point in the process, which means you never have to wear a respirator. You don't need any complex venting scenario or really many facility changes like you would with a powder bed fusion process. You don't need any third-party equipment. Everything you're going to need to get up and running and printing, we're going to provide to you. You don't need any dedicated operators. You can get trained with the system very easily. The software Fabricate gets you up and running very quickly. You just upload your CAD file, and it's going to walk you through each of the three pieces of equipment. You don't have any welded supports to your parts, which is, we didn't talk too much about this today, but with powder bed fusion, your supports are welded right onto your part. With this process, we actually put a release layer in between. We print a release layer right in between your support and your part, so that way after sintering, the part comes right off the supports. And like I said before, no special facilities required. This can really go into any office environment. I could have it here in my apartment in Boston here if I wanted to. I wish I did, actually. I should have brought one home before I went into quarantine. So looking at some of the benefits of the studio system across the product lifecycle, we're really seeing benefits across the entire life cycle, So starting just in product development, the ability to prototype, and not just, prototype form and fit, but actually prototype, for functional testing. The ability to put a part into our machine under high loading, under high heat and high chemicals really allows for a better product, allows you to do these design studies where you can iterate on your part very quickly. You can produce these display and demo parts. And then if you're thinking about, a pilot run, where maybe you're going to create 1,000 or 10,000 of this product, but you want to create 10 first so you can do an alpha or a beta. this pilot run, rather than having to go to that casting supply chain, we could simply just print these 10 parts and we're good to go. We can avoid that often long lead time associated with casting. In the manufacturing environment, doing lots of jigs and fixtures, end of arm tooling, things that are often required to be metal can be quite complex, but are almost always produced in low volume. Same with mold inserts and extrusion dies and stamping dies. These tooling components that are often quite expensive, long lead time, but almost always produced in low volume. These are great parts for the studio system. Looking at aftermarket, replacement parts, customized parts, and then this idea of that digital warehouse where rather than keeping a warehouse full of parts stocked, we're simply able just to print on demand when we need it. And we'll talk through examples of almost all of these today for the studio system. Looking at the business impact, right, of integrating the studio system, we're really able to reduce that product development timeline. Doing this by being able to do this in-house rapid design iteration. We're testing not just the form and fit of the part, but also its function. We're able to avoid these often lengthy machining operations that are required for some of the complex parts that we're going to look at today. And of course, there's never any tooling required for the studio system. We're able to lower our costs of parts, increase the revenue. We're able to really, oftentimes with the studio system, we're able to increase our manufacturing uptime. We're using the studio system to complement some of our other machines. We're producing the end of arm tooling, we're producing those jigs and fixtures. This frees up our machining capacity in our internal shop. You don't need any highly skilled, dedicated operator. And then this last one is probably my favorite, if I could pick one, but being able to optimize our part performance for the application. We're designing for what the part is being used for rather than for how it's going to be made. We're doing this by achieving, these very complex, intricate designs, and just for being able to produce parts that just are not possible using traditional fabrication methods. So another poll here, I'm curious to know what your average production volume is of a unique part. As your company is designing a part, you're setting it to be built. Are you building one of these parts? Are you building 100 of these parts? Are you building 10,000 of these parts? I'm curious just to know what your average production volume is. My colleague here should be opening up this poll. Maybe. Oh, there it is. Great. Just give you a couple seconds to answer this. Great, so we're looking at the results here. Some people doing one-offs, 2 to 10, 10 to 100. Great, so the reason I wanted to ask this is because now we're gonna get into talking about the shop system. The shop system is really, the world's first binder jetting system that's designed for machine shops. So what does this mean? It means it's accessible for all in terms of, both the cost and the usability of the system. It has unparalleled productivity in terms of, the throughput of the machine and how quickly it can produce parts, and it's really having that superior print quality, that high quality parts that you would expect from a machine shop. So we've learned to use these metal injection molding powders, so we're able to use these for both, the BMD process, which is what we were talking about on the studio system, and also in our binder jetting process. So both of these processes are using these binders that are then going to involve a sintering process. So a little bit about how the shop system works, or just binder jetting really in general. You can see on the left here with our jigsaw puzzle parts, we have our build box. Those jigsaw pieces are, analogous to a part. We have a powder box on the right. The roller comes and spreads a layer of powder across our build box. We then have our print head on the left here that's going to come across and print a layer of binder. Then the roller is going to come across again and lay down another layer of powder. And then, our print head comes across again and lays another layer of binder. So it's very similar to, if you think about, just an inkjet printer, but it's, each layer we're spraying a binder rather than, an ink. And we're moving down the build box to lay down another layer of binder on top of it. So once the parts come out of the, the printer, they're debound. or they're not debound, they're depowdered, and then they go into a sintering process, right? So the first step of the sintering process, we're going to go up to, do a thermal debind where we're going to remove that binder out of the part, and then we're going up to the temperature just below the melting point of the material, and we're going to sinter the part. That's how we're getting our highly dense part, and then we're able to cool uniformly, so we're not leaving any thermal residual stresses on the part. So here's just an example of a variety of parts that you get out of the, we're going to talk about some of these today, but just kind of getting your mind thinking about what some of the parts are looking like. Here are some more. At this point, hopefully my colleague Ilya will be able to show you some of his parts. If you can look at his camera here. This is the first time we're trying this, so thank you for bearing with us as we experiment with this new camera. You can see here some of the...
So here's just a range of parts. We have, this is a car customized shift handle. This is a parking brake bracket. You can make relatively small parts like this. You can make relatively complex parts with a shop system like that. Now let's actually zoom in. So you can really see the definition possible and the great surface finish. This is about 2-3 micron average surface roughness. And you can make all sorts of, so what all of these, whoops, let me zoom out. What all of these parts have in common, they're from a variety of industries, is that they're relatively complex. This would be either several components welded together or require machining with multiple complex setups, or if it's casting, you would have sliders, metal injection molding, you'd need to pay for the tooling. So parts like this can now be done effortlessly. And you can make small parts, you can make larger parts. All right, back to you, Ethan.
Awesome, thank you, Ilya. We'll hear from Ilya again soon as we talk about some specific parts. I'll be talking more in detail about. Ilya has those on hand to show. Didn't want to risk grabbing them from him. We're respecting the quarantine. So what does this allow you to do? So something like, with the shop system, something like a mixed volume production. If you look at the build volume here on the right, you can imagine asking your internal machine shop or whatever your favorite machine shop is to produce all of these different parts. Each one would require different fixturing methods, a lot of different machines. You'd have to cut stock, you'd have to then, do some lathe operations, some grinding operations, some mill operations, But with the shop system, we're able to produce all of these parts in just one simple build of the printer. It takes one, you can do it all in one shift. So you can imagine, something like that your shop is now able to do. You're able to produce a lot of different geometries, all in one build. Then you're able to do something like a mid-volume production, right? Where we're able to produce hundreds of these parts every day. We're doing this with a dramatically reduced labor cost. You're able to, a wide expanded, you're really expanding your geometry flexibility. Parts that would have been very difficult for your shop to make, you're now able to make, on demand, hundreds of them at once, and then just machine whatever critical dimensions you may need. So really reducing our costs with the shop system, right? We're eliminating our tooling. You're printing your parts without the needs for molds or any work holding fixtures. And, this allows us to really reduce our tool wear, right? Because, rather than having to cut out a big billet of material, for each part, we're simply just printing and sintering our part, to the near net shape. And then we're just doing, if even necessary, just doing a finishing pass on the part. We're reducing the labor cost per part because we don't need our highly trained, expensive machinist time. We're able to just get the printer running. The printer runs in the background, and then we're just doing simple, simple machining operations. We're able to reduce our job setup costs, of course, because we can set up our entire print build in just an hour or two, regardless of how complex the part is. Where, depending on how complex a machining part could be, hours of, CNC programming and, fixturing design and fixturing setup. Then really the ability to reduce manufacturing steps. If a part is taking your machine shop, 5 or 6 different, fixturing setups, different manufacturing operations, the ability just to print that part and, eliminate 4 out of 5 of those steps is a huge advantage with the shop system. Really leads to a reduced cost. Then, of course, going hand in hand with this is the ability to increase your revenue with a shop system. Now we're able to produce geometries that just we couldn't have done before, either because they were outside the ability of our shop, or they just are parts that are not, possible to machine. We're able to print these hard to machine materials like, tool steels that are just, they're not compatible with laser powder bed fusion, and they really wear on our tools and are really, you have to cut very slowly, but the printer doesn't care what it's printing. So, we're able to print these tool steels, these hard to machine materials, no problem. We can make, a wide variety of different job sizes, all economically viable, especially when it's something that's quite complex, because, we don't have to invest in this tooling. We don't have to take down a machine or, dedicate a machine to, producing just 5 of these parts when the volume doesn't make sense. Now we can just add those parts to a build volume, run the printer. This allows us to win that new business that we weren't able to take in before, and really free up our CNC capacity, allowing it to work on new jobs. So let's talk through some applications, look at some parts. I hope you now have a good idea of how both the technologies work, what some of the technologies are good for, and I think you'll see all those benefits today. So just looking at some of, Desktop Metal's customers, we have a wide variety of customers, some of the biggest companies in the world, down to some small shops that we're adding value to. We'll look at both today. This is just looking at the United States and Europe. We have, a wide variety of systems around the world. And, today we're talking about heavy industry specifically. So we'll look at some of these companies and, how they're using both of these systems. And when I say heavy industry, I mean, or what we mean is, energy, chemical processing, the construction industry, mining, etc. So that's everything from, like very large gears for big earth drilling machines to these custom manifolds and impellers, things like nozzles for chemical processing and pumps for, dirty fluids, heat exchangers that are also used in chemical processing, and, like fuel atomizers and oil and gas. And so we'll look at a lot of different parts today, but, just getting your mind thinking about, where can you be using these systems in heavy industry? So let's start with the roller screw. The roller screw, this is a part of a roller screw linear actuator. It's actually opening and closing a pilot valve in a power plant, in a steam power plant. This was a part that when initially was designed, needed to be manufactured out of 7 components and then all assembled. So with the studio system, we were able to prototype this part, simplify the design all into one part. Prototype it on a studio system in just 4 days, costing us $86. And then now we're looking to mass produce it on the shop system. So we're able to, validate the design, not just the form and fit, but actually put these parts into the actuator, load the part up to a couple thousand pounds to make sure it's able to push that valve open and close. And then once we're happy with the design, we're happy with the function of the part, we move to the shop system where we're able to, get the cost down to only $51. We can produce about 240 of them per week. So if you look at the comparisons, what it was going to cost the CNC shop to make this part, huge cost savings, and the ability to functionally prototype was something where the systems really added value here. You can see, the original design, 7 parts that involved some, set screws and involved some welding process, able to print that part all as one. Looking at a downhole tooling slip. This is an oil and gas component. It's a little bit confusing what it does, but what it does is, you drill a pipe into your well. You're then able to lower your actual pumping components into that pipe. These downhole tooling slips actually expand out and hold your pumping components inside of that initial pipe that was drilled. There's still quite a bit of development going on with these because, depending on which pumping scenario you're in, different tool slips are better or worse for each of those applications. So this is just an example of a patent that was, recently written for these downhole tooling slips. So like I said, this part is holding a frictional hold. Again, they were able to prototype this part in the studio system, where rather than just form and fit, we're actually able to print these parts in metal. We're able to put them into this high loading scenario and understand which geometry is best for, the individual pumping scenarios. We're then able to move to the shop system for actually mass producing these parts. For just $81, we can create these downhole tool slips. About 198 parts per week. This part is actually lost after the pumping is complete. So, the ability to keep the cost of the part low and, the lead time short is very important with this part. And I believe Ilya here we're doing another Ilya part showcase, as I'm going to call it. And he has one of these, I believe, for both the studio system and the shop system that he can show us.
So here's one from this is from the shop system. This is from the studio system. This one was polished so that there's inserts that get brazed in here, and so it may actually be functionally beneficial to have the smooth finish. So that was a test. And then this is a part designed produced on the shop system.
Awesome. Thank you, Ilya. It's like my magician's assistant today. Appreciate it. Great. Let's keep moving. Bulb nozzle. This is a nozzle used in a chemical process. It's spraying a chemical. So this is a custom nozzle that's used in chemical processing. The traditional manufacturing of this part required, the part to be cast, followed by, extensive secondary machining operations. By switching over to the shop system, the part was needed in about a quantity of 100. We're able to manufacture, the entire order of nozzles in less than a week. And, rather than needing this extensive 5-axis CNC operations for each of those little holes, we're now able to just do one secondary operation, which is simply just tapping the thread on the bottom of this part. You can see with the shop system, we're able to produce this part for about $29 per part, and it's costing us $29 per part, and we're able to do about 320 of these per week. So huge cost savings here on this part. Just a little bit about how the costing is generated too for the shop system. This is including, all your consumables, electricity, labor, depreciation of your system. So it's really a fully burdened cost here, just for, your knowledge and your reference. Heat exchanger. This one features a helical conformal cooling channel. So this is a part that, it's used for cooling fluids in a chemical processing. Since since we're printing it here, we're able to design the part for its application rather than for its manufacturing method. This features an internal cooling channel that wraps up the entire part in a helical form. This allows us to get a very high heat transfer rate, right? And we're also able to incorporate these fins into the part that are allowing, that increased surface area, excellent thermal conductivity out of copper. We're able to produce a very high, very high performance part. Working with copper too, we're able to just print it and sinter it rather than having to deal with, some of the difficulties of machining copper. And, copper is something that's, not possible to make via powder bed fusion. Studio system, able to print the part for about $440. Just took us 4 days, just to machine this part without the internal cooling channel, costing us, $2,100 and taking about 2 weeks. So huge advantage here. You can see, the internal cooling channel being printed here since we're moving up layer by layer. Then you can see, the final green part here in the middle, and then the final part here on the right. Impellers. So, different impellers are sometimes desirable depending on, what fluid is being pumped. You want to optimize these impeller vanes, to get you a specific pressure, a desired flow rate, depending on what fluid you're pumping. These vanes are often, very difficult and expensive to machine. They feature some thin walls that might vibrate during the machining process. They also have some natural curvature that means you probably need a 5-axis machine. This makes prototyping of these parts, very expensive. By printing this part, we're able to, rapidly functionally prototype these parts. We're actually able to, print these impellers, get them spinning in our pump to see how they to see how that geometry works with these corrosive fluids, or highly viscous fluids, to understand how that different geometry is leading to what pressures and what flow rates of our of our fluids. So the first impeller, this was made out of 316L. That was the desired material for its corrosion resistance. The other impeller was used for an oil and gas operation. This was actually made out of alloy 625 for Inconel, allowing the part to, have excellent heat and corrosion resistance. I think we're going to do another Ilya part showcase here. Hopefully this is working well. He has these parts on hand for us, and we're going to take a look, and you can really take a look at some of the complex geometry that these parts feature.
Let's see. All right. Let's zoom out. Here's that part. Here's its friend, the other impeller. You see this one is right off the printer, right out of the furnace. And this one was finished with isotropic super finishing process to make the finish dramatically smoother. So this is a couple micron RA average surface roughness. This is more like 100 nanometer roughness, so 20, 50 times smoother.
Great. Thank you, Ilya.
You bet.
All right, looking at a sensor holder. So this is a part that was produced on the shop system. This part holds multiple sensors in place, in a precise machine, making sure we're able to have the sensors exactly where we're needed so they can take accurate measurements of our running machine. This part has many small details to hold these small sensors, makes it very difficult to machine, or, very complex metal injection molding process. Being able to print this part on the shop system, obviously we're able to greatly reduce our manufacturing lead time. We're able to print, hundreds of these per build, and we're greatly reducing the cost. Another benefit here is since we're not incorporating any tooling, we're able to, modify the part on demand. If we want to incorporate different sensors into our machine, we want to upgrade a sensor, we're able to modify our design. We don't have to change any tooling. We simply just send the new file to the printer, and, that same shift, we're ready to put parts in the furnace. The cost here, you can see we're able to do each one of these parts for, about $8, able to do about 1,500 of these per week. So you can imagine, asking your machinist at your company to machine one of these for you out of 17.4 steel and, ask them to do it for $8. So we're really able to get that cost per part low, especially with these really complex, smaller parts. Looking at, this is a hydraulic brake housing. We looked at this part a little bit earlier, but, you can see on the right, the original cast component. On the left, we have the one that was printed on the studio system. So this component, it's part of a large articulated truck. It's holding different, hydraulic brake components. The part was traditionally manufactured via casting in high volume. They then did some, machining of the critical dimensions. But, when a replacement part was requested, the casting line was no longer operating. So they needed to find a new manufacturing method to be creating these parts, right? Because a customer calls, they say, I need a new one of these brake housings. Ours unfortunately broke. We need to get this truck back up and running. So rather than trying to find a new casting supply house or, pay for the very, very expensive machining operations and long lead time, we're simply able just to print this part. This is, obviously cutting down on the manufacturing lead time. We're doing it for just about $900. This is quite a large part if you look at it next to the quarter here. Ilya, I believe he has this part as well. I don't know if this one's going to fit under the high def camera, but he has
It's gonna fit.
But he has it to show to you, I hope.
Here it is.
Oh, I'm sorry. I minimized my camera.
Well, you never minimize it. Look at this gigantic part. Huh?
Right. So the ability to print that on the studio system is, huge advantage. Simply just, avoid that casting supply chain, print that part, machine any criticals that may be necessary. We'll keep moving. Looking at a bearing housing. This is a housing. It held some press fit bearings in precise locations in a machine. The part needed to be, the real value that was added here was the part needed to be produced very quickly and out of steel. So, utilizing the shop system, all the parts could be printed in just 2 days. They're ready for assembly in less than a week. The manufacturing process required almost no operator labor, very accelerated manufacturing lead time. You can see that, on the shop system, the part cost was about $73. We can do that for about, 192 parts per week. With the CNC operation, were costing us about $162 per part and taking 2 weeks. So the real win here is the speed that we're able to produce. Since we're having to rush machine these parts, we're getting a huge cost savings by simply printing all of these on the studio or on the shop system, machining any critical dimensions that may be required. We're able to really, really accelerate that manufacturing lead time. So let's look at some case studies now, look a little bit more in depth at some of the customers we're working with. Starting with Master Drilling. Master Drilling is located, down in Johannesburg, South Africa. They make these, they do make these very, very large earth drilling machines. You can see one here drilling, miles into the ground for mining operations. So they had a problem. They have these planetary gear sets, these attached to a motor that are attached to a drill bit to increase the torque and the spin rates of the drill bit. This internal sun gear unfortunately broke. They needed a replacement part. They were currently building that part at a foundry in China that was taking them about 3 months per part. With the studio system, they were able to print the part, debind the part, sinter the part, case harden the part, and do the critical machining operations in just 3 weeks. So this was a huge win for them, right? Because they were able to go from a 3-month lead time from their foundry to simply just 3 weeks down to 3 weeks total with the studio system, and that's including this case hardening operation and this machining operation. So they're able to get their drill back up and running. They're able to, when the drill's down, they're not making money. So this was a huge advantage for them. This is a very big part. Again, you can see it here on the screen next to a quarter. I won't have Ilya show this one just because I don't want to keep you too long today, and we still have a lot to talk about. Ewell. This is a company in Italy. They're founded in 1997. They're a leader in the high-tech marine propellers for sailing yachts. They use a lot of stainless steel, for its very high performance, its excellent mechanical properties, and its corrosion resistance. So this is a part we're looking at. It's a propeller pinion. This is a part that they were traditionally investment casting on a 17.4 stainless. They were having some issues with this investment casting process because, with the investment casting process, in order to make it economically viable, they had to produce it in a 100-part lot. So when they needed a low volume of this part, the cost was far too high. So they looked to the studio system to see if they could print this part and avoid this investment casting supply chain. It also required some complex machining operations even after investment casting. The internal ribs and the deep internal channel was quite difficult to machine. So they were looking to really iterate on this part and produce it on the studio system for avoiding this investment casting supply chain. So you can see here on the left, you can see on the right is the part right off the printer. On the left is the part after sintering process. They simply just machined the critical dimensions on a simple lathe rather than having to spin up a 5-axis machine like they would normally use. This led to huge cost savings, huge time savings. They're able to avoid this investment casting supply chain. They're actually able to improve the part quality as well. They found, compared to what they were getting from investment casting, they can design the part for its application. So they can, design these pinions for the specific yachts rather than having to use the generic one in the quantities of a couple hundred. So this was a huge win for them by using the studio system. So the business impact for Ewell, they're really able to avoid this investment casting supply chain. So they're really looking to now move to higher volume production. They're really trying to avoid this supply chain, so the casting supply chain. So looking to move to the shop system to produce these parts in a higher volume. Cifarelli, also located in Italy, founded in 1967. They're a leading vendor of agriculture and gardening equipment, and they have a rich history of technology and product innovations. They're always looking to add to their manufacturing technology. They use these shaker hooks. These vibrate at over 2,000 vibrations per minute. They have a stroke of 62 millimeters, which is actually quite high. This is used for shaking a branch, to harvest fruit or olives. The geometry is very important. It has to be very specific to ensure that it doesn't damage the tree, and it adequately shakes over 95% of the fruit off of the off of the tree. So, this part was originally built, via aluminum chill casting in the quantities of, a few thousand, but they get some custom requests for some of the lower volume stuff. So this wasn't economically possible, right, with chill casting. So they were looking for a low volume method where they could really design the part for its application rather than for its manufacturing method. You can see they decided to go down the route, once they decided they were going to 3D print it because that was going to make the most sense for the volume, they went down the route of creating a part via generative design. So you can see here they're optimizing the part for its application. They want it to be strong only where the loading is, only where it needs to be strong. This is also going to be able to lightweight the part. So you can see here 2 of the parts that have been the generative design is finished. They printed the parts, sintered the parts, and they're ready to test. Hopefully my video works here, but you can see this part. Awesome. So for Cifarelli, the big business impact, right? They're able to produce a part that's much stronger at the same weight as it was in aluminum. This has a huge advantage because they're able to take weight off of the gearbox, which is leading to a higher performance part, a more reliable part. They're able to, do these low volume customizations for specific applications, such as what we just looked at. And then in the future, they're really looking to both move to higher volume with the shop system, but also explore across their entire product line, where they can integrate 3D printing to really improve the performance of each of their different products. John Zink, Hamworthy Combustion. So John Zink is a leading vendor of emission controls and clean air combustion systems. They had an additive initiative. They rolled it out in 2016, where they really saw a lot of companies utilizing the benefits of additive manufacturing, and they wanted to integrate that into their company. The way they did this, they purchased 13 Ultimakers. They located them throughout all of their manufacturing environments, all of their different offices around the globe, and they really encouraged their employees to print things not just for their business related work, but also personal things. They wanted to get people familiar with additive manufacturing. They wanted to get people using additive manufacturing. They then purchased a desktop metal studio system, and they got up and running with metal 3D printing. So what is John Zink using the studio system for? They're printing, jigs and fixtures, custom tools and dies. They're also, they produce these very large machines that they ship to customers. The customers, use for up to like 100 years. So they get these urgent aftermarket orders where a customer has a part break. They need a replacement from John Zink very quickly. So they're using the studio system to produce those parts, and we'll look at some of those examples. They're also, of course, doing prototyping parts for testing, where they're testing not just the form and fit of the part, but they're actually testing it under high loading, under high heat, under corrosion. And then, they're also, of course, printing parts that just can't be manufactured using traditional methods that can only be made with additive manufacturing. So here's an example of a UHT atomizer. This goes onto a liquid natural gas tanker. It's used in the burner for steam propulsion that actually is propelling the ship forward. They realized that at low speeds, this burner doesn't work very well. It only has a 15-to-1 burner turn down, which results in very, very poor fuel efficiency. So John Zink was tasked with, how do we create an atomizer that's going to get us a better performance at this low burn rate? So they went through some design iteration. They realized very quickly that that with the volume that these need to be produced, and they decided to design for additive. This allowed them to design for the application, not for the manufacturing method, and able to really optimize these internal pathways to improve these low burner performance. So if you see here a couple of different of the design iterations they went through, we're varying the geometry of that internal channel. We're varying some of the angles that the channels are coming out at, all trying to improve this burner performance. You can see here a couple more design iterations. On the far right is the final design. So they ended up going with the final design of the studio system here, printing in 316L. stainless steel. That's giving them this excellent mechanical properties at the high temperatures it's operating at, the excellent corrosion resistance that was required. And then they were able to increase this burner turn down on this part from what was originally the 15-to-1 on the very simple atomizer to 25-to-1, which was a 67% improvement. This led to a customer fuel savings of about $90,000 to up to $160,000 annually. So a huge cost savings by simply integrating a few of these different burners or atomizers. So on the studio system, they were able to produce the part for about $300 in 5 days versus the DMOS option was about $1,200 and taking them 8 days. So this was a huge win for both 3D printing and of course for the studio system. And I think Ilya has this part on hand for us to show as well. There it is. So this is a very cool part featuring these complex internal channels that are snaking up through the part that are really optimizing this this fuel output. I want to show us the bottom of that as well, just so you can see the internal. Awesome.
Yeah, and these internal channels curve, and as you can see, they're slotted, and so this would be an impossible geometry to create with any other method.
Great, thank you, Ilya. Moving on. Oh, you can see here just the atomizer as it's actually firing in the engine. It's quite a cool part. So another example. So for their aftermarket orders where they just no longer have the hard casting tools, they did some work on this, USS Blue Ridge, a naval ship. They got a request for a replacement yoke and some handles on some shutoff safety devices. Rather than having to, pull one of their machines or CNCs, off of the job it's currently working on for this urgent order, they're simply able to just print the part in a few days, get it out to their customer, they're back up and running, they're happy, rather than having to, really go into the supply chain. They can take it all in-house and do it all themselves. This is a YE6 burner tip. This is a great part. This is a part, if you look at the drawing here, was produced in 1967, so over 50 years ago. They got a customer who called them up. They said, we need this part. It unfortunately broke. They were able to, the casting house, obviously, that produced this part 50 years ago, no longer operational. It's a part that, can't be machined because of some of the internal channels that were involved. So they were simply able to, spin up the studio system, print the part, sinter the part, in less than a week. They send the part out to the customer's back up and running, and the customer's, quite happy. So you can see here, studio system able to produce this part for just $193 in just 7 days. An SLM version of this part was going to cost, $6,500. So great win, be able to do it far more affordably, far faster than what we'd be able to do with, other manufacturing methods. So business impact for John Zink. They were familiar with metal 3D printing from powder bed fusion, but really only saw it as a last resort. They saw it as being very expensive, very inaccessible. But with the studio system, they're able to introduce this low-cost metal 3D printing. They're able to take their designs to market faster by doing these design iterations and without the need for tooling, where they can actually functionally test the parts rather than just, does it fit? They're avoiding the tooling costs for these low volume parts. Then they're able to do much faster turnarounds for their casting parts, especially when it comes to a replacement part. So what's next for you? Thank you very much for coming today. I hope you learned something. I hope everyone is staying safe. What we'd love to do with you is we'd love to explore what additive can do for your business. We'd love to set up a one-on-one meeting with you and a metal 3D printing specialist. Here we can explore what metal 3D printing can do for your business. We'd love to look at your manufacturing environment, your parts, see how we can add value. We're happy to give you free part assessments if you want to send us a part. We're happy to look at that part and tell you if it would be a good part for our process. If we could print that part, how much it would cost and how quickly we could print it. And then if all the numbers are making sense, we're happy to provide you some free samples and really talk about how we can add value to your manufacturing environment, to your company. I have one more poll here. Love to get your idea of, what would you love to see more of? We're going to be doing a lot of these webinars. Unfortunately, a lot of us are working from home right now. So we'd love to know what you'd love to see more of so we can make sure we're really tailoring this content to you, making sure something specific to you, something that you're able to learn. Thank you so much for coming today. I'm happy to answer any extra questions if you want to reach out to me via email or if you just have any thoughts or comments. I hope you learned something today. I hope everyone is staying safe. We're going to be doing a lot of these webinars this week, so if you head over to Desktop Metal website on the events page, you can see all the webinars we're going to be doing this week. This is kind of our learning week, taking advantage of everyone being home and hopefully opening to learning something new. I really appreciate you taking the time to join me today. Thanks so much, and I hope everyone's staying safe.
Just a couple more questions we're answering.
Great, I can see if I can hop in to help out.
Nice questions keep coming.